Hi, and welcome to Data 602 Advanced Programming Techniques. In this session, we're going to be talking about regression. If you're not familiar with regression or need a refresher on what it is, this is a session you should spend some time with. If you're using regression fairly heavily or are very familiar with it, then you may wish to skip this video. So let's get started. So what is regression? Regression, formally defined, is a statistical method used to determine the strength of the relationship of a variable to one or more other variables. Now, what does that even mean? And the best way I can explain it is to look at the problem that it is trying to solve, or the intuition behind regression, and that should help us understand what regression is and why we need it. And in order to do that, we can start off with a simple stock chart, where we have a stock that, let's say, just IPO'd or just was released into the stock market. We can see that on day 0 the stock closed at $25, and we're plotting its closing price, and on every subsequent day, so day 0 is the IPO day, day 1 is the day after the IPO, it closes at $45, and so on and so forth. And this relationship between the days and the price is what we call linear. You can see that this is an inclining straight line, meaning the line is increasing at a predictable rate. You can see that it goes up and seems to be going at a rate that is constant. Now this can be represented in an algebra form, and this is the equation that we use, and it should be familiar to many of us. Probably have seen it in high school. At the top is y equals mx plus b, or the second equation below, y equals b0 plus b1 times x. Both equations are identical. Both describe a linear relationship between x and y with a constant slope. In other words, these algebra equations can represent a straight line on a graph that has a constant inclination or declination rate. So for this video, we'll be using the top notation because people may be more familiar with it. And so now let's examine and break down this equation for those who may need a refresher. The first variable in this equation, x, is in this scenario the days of the stock, or so meaning day 0 or day 1, x would be 0 or 1 respectively. Here x is referred to as the independent variable. That means it can really take on any value that it wishes. It is not tied down to any other value or any other variable value. And in case of the chart we just looked at, x here represents the x-axis and the values that are on the x-axis. The second variable here is the y variable, and plays the role of the dependent variable because it depends on whatever the values are contained by the variables to the right of the equal sign. So whatever x is, whatever b is, will all impact the value of y. Y is kind of beholden and dependent upon everything to the right of the equal sign. On the stock chart, y is the price of the stock. Now b is known as the offset or the y-intercept, and it's the value that y has when x equals 0 or at the point where the line crosses the y-axis. Finally, here m represents the slope. The slope is the rate of incline or decline of the line. In linear equations like this, the slope is a constant. In the stock chart, we can reasonably assume that the slope is a constant because the incline seems to be going up at a steady pace. We can claim that the slope is constant, and in the y equals mx plus b world, m is assumed to be constant. Now we can quickly go back to the chart and try to take this line and derive the algebra equation that represents the price movement. While we do that, we can start off by first figuring out what b is. B is, if you recall, is the point where x equals 0, where the line crosses the y-axis, and we see that this line crosses the y-axis at $25. And so what do we do is basically substitute b with 25, because that is the value of y when x equals 0. Next, we'll try to calculate the slope, or m. And the slope is basically delta y divided by delta x. That is the difference in y divided by the difference in x. And in this case, we can take any set of data. We'll just take the first set of pair of values here. which will be day 0 and day 1, and we'll calculate the delta of y, which is $45 minus $25, and then we'll calculate the delta of x, which is 1 minus 0, and this gives us $20. So every day moving forward, the price of the stock goes up $20, starting off at the base price or the offset of $25. So in this full algebraic equation, we can see that y equals 25 plus 20x, or y equals 20x plus 25, and this is in the y equals mx plus b format. And if you wanted to verify this equation to see if it jives with the stock price line, what we can do is we can substitute x with 0 and then put in b, the offset at $25. And then we can calculate that out, and we'll see that actually y turns out to be $25, and we can look back at the graph and see that this does check out. We'll also substitute x for 1, see if that also works, and we would see that the price would be $45. And so when we did 0, it did come out to $25, and we put x into 1, y came out to $45. And we'll just do one more just to make sure we can do it also for day 3 and see the stock price for day 3 is $85. And we can confirm that on the graph that the price for day 3 is in fact $85. So this is all wonderful stuff, but not necessarily very realistic. What happens if we have a stock price chart movement that represents movement that looks like something like this? Something like this is more realistic and representative of stock price movements. Stock price movements are random, so it can go up or down and does not have a consistent or constant slope. This type of line would break the y equal mx plus b mold. So can we derive an algebraic equation for these data points and this up and down volatility? We can't do that directly, so what we can try to do is try to produce a line that gives us an estimation. So we might want to draw a line that gives us an estimation. So for every x, it might give us an estimated y. Let's redefine regression as fitting a line to a set of data points so that its linear algebra formula can best predict the outcome of y as a function of x. So what is considered best? So let's say I go back to the stock chart and I draw a line. Is this the best line? We can start drawing lines that give us estimations. And let's say I plug in 2 for x and I get out a y that's somewhere around here, which is, let's say, around $33, and the actual stock price is, let's say, around 31 or 32, and I can say, well, this line does give me a close approximation of what the stock price would be, but then I have a problem here on day 3. This line would predict something around $35 or $36, where in reality the stock price was around $21, and the gap between the two is fairly large. And the gap here is not as large as here, and then the gap shortens here, but doesn't necessarily have to shorten. The stock price here can go down, and then the gap would start to widen. And I can move the line down and say, hey, you know what, maybe I should try a line here, and I do that and I put in A3 and say, voila, I actually fixed the problem. Now that my line here is predicting for day 3 something around $19 or $20, and the stock price, the actual stock price, is somewhere around $21. This line has fixed my problem. However, if I punch in 2, I see that it produces a prediction of around $18, where the actual is above $30, and now there is a gap here. I can kind of calibrate this. Let's be smarter. I'm going to move the line to the middle and play around with this. But is this the most accurate? Should the line be here, and should it cut through the middle through here? Should I, cut through the middle here? And how do I know which of these lines that's cutting through the middle seems to be like more fair or better fit, but which one is actually accurate? And how do I measure that? To do that, we can use an algorithm called ordinary least squares, or OLS. And what OLS does is it gives us a way to best fit a line. Now, what do we mean by best fit? This is kind of a subjective term. However, with ordinary least squares, what we want to find is a line that on average has the shortest difference between all the points in the line. So let's look at this, what this looks like. Now I have, let's say I draw a line across here, and what I do is I try to figure out what the gaps are. And so I'm looking at these gaps and these orange lines, and I can do is then add up the gaps and try to find a line that has the lowest number of total gaps. So just kind of like add up these the length of these orange lines and try to find the smallest number. That would mean that this would on average have the smallest gap between this line and all the data points. Now OLS does a few more things because these differences can be negative numbers. So this is a higher number, this is a low number, so the difference might be positive or negative. So what we need to do is we square that. So we add a couple of steps just to clean out the data. So what we do is we draw a line, we just draw a line randomly, and then we find the distance between each point and the line like we did with the orange lines, and then we square each distance. By squaring it, we get rid of the negative sign. Everything is positive, and then we sum up all the squared distances. So then our objective is to continuously to repeat and do that over and over until we found the minimum sum, meaning that the sum is the lowest we can possibly find. And what that would imply is that we've got the most, we would have the best fit line. Now, how would we do this? This is what computers are for. A computer would keep drawing lines. You could draw millions of these lines, at least from a calculation point of view. It's going to create these lines and then calculate the sum of the squared differences and eventually arrive at the lowest number. And that is what OLS is. And we can use linear regression. This is in Python by using the linear regression class from the sklearn package. And we can also do the same using the lm function in R. So with the linear equation, we may be able to predict y for a future x. However, are we now able to trade on this? Are we now going to be filthy rich because we figured out a way to predict stock prices? There are pros and cons to using regressions. One of the problems with regression is that if there is a significant departure from this trend line that we've kind of identified using OLS, if there's a significant departure, whether from on the downside or on the upside, then this entire algebraic equation that we use regression to arrive at kind of goes out of whack. And is not necessarily usable. If there's a huge upward movement, then this line may not be able to predict it. However, we can use this line to possibly predict things within the data set. So let's say we've retrofitted this line into data points that we've given into the linear regression class in Python for days 0 through 8, and it's produced this for us. We can, with some accuracy, pick data points in between 0 and 8 and get some accuracy in regards to that. However, going beyond 8 can produce, there is a significant risk that we would not be able to predict the right price. So picking data points within the data that we've used to get at this line is called interpolation. Going outside of this is called extrapolation, and interpolation is typically more accurate than extrapolation. That's one of the negatives of using regression. Regression is probably one of the simpler algorithms that we can use for in machine learning.